Okay, so let me try to. Oh. Yes, good morning, everybody. So my name is Zhongping Jiang. I'm professor of electrical computer engineering at NYU. So today is my great pleasure to introduce, Professor Francesco Bullo, our ESAIM speaker today. For those who are members of IEEE Control Systems Society, so you all know, Francesco, who was, our former president of IEEE Control Society. So for those who, do not know him yet, so let me, introduce him formally. Francesco Bullo currently is a professor with the Mechanical Engineering Department at the Center for Control, Dynamical Systems and Computation at the University of California, Santa Barbara. He was previously associated with the University of Padova, the Caltech, and the University of Illinois, or the Urbana-Champaign. He served on the editorial boards of IEEE, SIAM, ESAIM journals, and as IEEE CSS president and SIAM CST chair. His research interests focus on network systems and distributed control with application to robotic coordination, power grids, and social networks. He's also of the book, Geometric Control of Mechanical Systems, published by Springer in 2004, Distributed Control of Robotic Networks, Princeton, 2009, and the Lectures on Network Systems, published in 2021. He received Best Paper Awards for his work in IEEE Control Systems, Automatica, SIAM Journal on Control and Optimization, IEEE Transactions on Circuits and Systems, and IEEE Transactions on Control Network Systems. He's a fellow of IEEE, IFAC, and SIAM. So without further ado, so the stage is yours, Francesco.
Thank you, Zhongping. Thank you so much for the kind introduction and for the exciting invitation. I'd like to share with you today some ideas on contraction theory and how they apply to network systems. I will start by acknowledging and thanking my collaborators, Alex Davydov, a PhD student at Santa Barbara, Saber Jafarpour, a postdoc at Georgia Tech, and Anton Proskurnikov at Torino and Russian, all of the Russian Academy of Science. The papers are in the archives right now, and shortly after the talk, I will put them on my website. I will mainly focus about ideas on our recent NeurIPS paper and transactions submission. So if you look at, in 2012, there was a paper by Hinton and co-workers, which demonstrated a breakthrough in the accuracy of image recognition based on a highly structured, deep convolutional neural network. That marked the start of an exponential growth of papers in this area. And while feed-forward neural networks are extremely interesting and powerful, one may take inspiration from biological neural networks, whereby interconnections are certainly not of the simple feed-forward type. So the aim of the second half of this talk, the application side, is to understand the dynamics of neural networks in such a way as to model and analyze and obtain models that have reproducible behavior to some extent, that are robust in the face of uncertain stimuli and uncertain dynamics. And then lead this all the way to then studying learning models, efficient computational tools, periodic behaviors, and so forth. And the fundamental claim of this talk is that, in fact, contraction theory provides to you with tools that allow you to tackle precisely this list of challenges at the intersection between artificial and biological neural networks. So in other words, just writing down some formulas. On the left, you see the standard model of a feed-forward neural network with k layers, an activation function capital Phi. So Phi in what follows will be a nonlinear diagonal map. By diagonal, I mean to say it takes a vector as an input, but each output is an application of a scalar nonlinearity on the input. And on the right, you see an implicit model in which the state of the neuron, the hidden state of the neural network X, is the solution of a fixed point equation, and in which you see, as illustrated, and I will be more specific later on, the neurons are all interconnected with one another, including both self loops and feedback connections. And so I'm interested in doing this transition, studying implicit and recurrent neural networks. I'll motivate that better later. And I'm interested in studying fixed point strategies for these implicit problems. And fixed point strategies have, the study of fixed point strategy in the context of something called monotone operator theory is a set of tools that has come to the fore in recent years, because it provides a simplifying, unifying framework to model, to analyze, to solve a broad range of optimization problems, the generalized convex optimization, Nash equilibrium, variational and monotone inclusions, and so forth. It's just a generalized version of fixed point strategies. Now, let me start by talking about the first of the two topics, contraction theory. I'll have a short detour and then I'll get to neural networks. That's the outline of the talk. So contraction theory has a truly wonderful history. About 100 years ago, Stephen Banach had his first paper. A few years before, in 1906, Alex Markov was establishing Markov chain, proving convergence using contraction ideas. Another notable paper 50 years ago, Banach's paper was 100 years ago, is by Disor and Aneda, which showed actually very much related ideas to what I'm talking about today, a truly early remarkable paper. Then there was a landmark paper in '98 by Lohmiller and Slotin, who brought back to controls the concepts that were introduced years before. And that illustrated how powerful this language can be for dynamical and control problems. And by now, there are a number of surveys and tutorials available. For example, the one by Aminzadeh and Sontag at CBC 14, which inspired the results that I will show you today. The one by Di Bernardo and Russo's groups, and the recent one by Dr. Slotin, Chang, and Tsukamoto. So now, let me make a couple of comments about the history before I get into the mathematics. Contraction theory have been studied under very many different names. And that's one of the, if one wants to say a historical weakness, because the results appear to be, are not as cohesive as one might want. Here are 7 references where 7 different names are used for exactly or very, very closely related concepts. By the way, I will be adopting the standard language numerical analysis of one-sided Lipschitz map. This is a highly well-cited book in that area. It pretty much inspired also by the work by Disor and others. And these are all 7 sets of conditions on integral conditions on the vector field that do not involve derivatives on Jacobians on it. Whereas many of you may know that contraction theory for ODEs often involves Jacobians. So there are, perhaps an equivalent name of an equivalent number of other names. Now, one of the key points I want to make is that contraction theory is closely connected with infinitesimal contraction theory for ODE for dynamical systems is closely related to fixed point and to monotone operator theory and convex optimization. Here are some books that illustrate what I mean by those fields. So let me get started. So I think you're all familiar with the concept that you may have a fixed point problem, and if your map is a Banach contraction. If the Lipschitz constant is less than 1, then the map is a Banach contraction, and you can apply the Picard iteration, which comes with numerous properties in order to compute a fixed point. But what if instead you're given a map whose Lipschitz constant is greater than 1? Can you do something in that case? It turns out that you can consider, I'm going to refer to this as the average fixed point algorithm, the average iteration. where there is a step size alpha. And it turns out there is a little known result, certainly not stated in the way I am right now, saying that there exists a step size alpha such that the average iteration is a Banach contraction, if and only if a naturally associated dynamics is infinitesimally strongly contracting. So in the ODE sense, in the dynamical sense. And alternatively, in the language one-sided Lipschitz constant, which I'll talk about, those constant, the constant is less than 1. Now, I will spend a few slides telling you what one-sided Lipschitz constants are and what does it mean for a vector field to be infinitesimally strongly contracting. But the one key point here is that if you want to design an iteration, which is a discrete time fixed point map, then you want to study the ODE associated with the problem. So that's a remarkable little point. Now, I don't want to spend too much time, but fixed point theory and contraction theory comes with many robustness guarantees. Imagine, for example, that you have two different inputs. So your input is corrupted by some noise, perhaps. The second input V is distinct from U. Then the variation in fixed point is described by a Lipschitz constant as sensitivity and input-output gain times the variation in the input. This result here is a standard Lim's lemma, well known in fixed point theory, but this too can be extended to use one-sided Lipschitz constant. It's a stronger result here. It handles, so the coefficient at the denominator here is in general better than the one up there. And you can handle both variations, in uncertain data, in U becomes V, as well as unmodeled dynamics. So it's really a robustness result, the way we would call it. In fixed point theory, people refer to this as a stability result, the stability of the fixed point when perturbations in the data and in the map are applied. I'll come back to this at the end because I will precisely use this robustness results for analysis as well as design purposes. Now that I've given you just a quick reminder of the discrete time fixed point Banach contractions, let me talk to you in detail about what does it mean for the dynamics to be contracting or fully sped, infinitesimally strongly contracting, just to make sure that we don't get confused. So basically the answer is that for all time t, the flow map at time t is a Banach contraction. And so here I'm showing two trajectories, any two initial conditions, and as you see, the distance between them is decreasing exponentially fast with rate minus c, where c is a positive number. And another detail in this image is that I am drawing my my unit disk balls centered at the around the trajectory x. I'm drawing them as square because I'm actually using infinity norm. So one of the points I'm going to make is that infinity norms are a proper strategy to use if one wants to understand input-output gains. Infinity norms. All right. Contracting dynamical systems have very highly ordered transient and asymptotic behavior. If the vector field is time invariant, they have unique globally exponential state with two natural Lyapunov functions, so really powerful consequences. If the input is periodic, contracting systems entrain. So this is a way of immediately establishing the periodic behavior of a highly complex nonlinear system. I don't know of other tools that do this. Contractivity rate is a natural measure indicator of robust stability. So that coefficient in the robustness results earlier is closely related to the contraction rate of the dynamics. They were studied in the numerical integration literature because they lend themselves to the design of accurate numerical integration algorithms. But the part that I'm most interested in today is the fact that for contracting vector field, it's easy to design algorithms to compute their equilibria. And the equilibrium of the vector field is a fixed point of a translated map, as you will see in a second. Now, I define contraction as two trajectories coming together. Let me give you some checkable tests. For that, I wish to introduce the notion of one-sided Lipschitz maps. These are maps whose derivative is upper bounded. It's not the norm of the derivative. This is a scalar map. and it's just an upper bound. So that's a one-sided Lipschitz bound. A two-sided Lipschitz bound would be if I were to put the absolute value of the map being upper bounded by B. One can easily show several things. One is that, well, you can rewrite that upper bound in this form as if it was an inner product on the left. X minus y dot fx minus fy is upper bounded by a quadratic form, by something quadratic, right? It's easy to see it's the same property. And that's the version that generalizes to higher dimensions. One can show that in a Lipschitz constant, the Lipschitz constant has to be non-negative, but the one-sided Lipschitz constant can be negative. It's a strictly decreasing function, not a problem, right? Okay, so how do I generalize this back to Rn, to Rn, and let me work with the weighted 2 norm with P is a positive definite matrix, right? And I, for simplicity, drop the time dependency. So then I will say that my one-sided Lipschitz constant is upper bounded by minus C, or equivalently, but then my map is strongly contracting with rate C if any one of the following 2 conditions, which are equivalent, holds. The second condition, for those of you who are control people in the audience, is a well-known Krasovsky condition saying that the P positive definite matrix is a Lyapunov matrix for the Jacobian of the vector field everywhere in space. The first condition is the condition that says that the it's the natural one-sided Lipschitz condition with respect to the weighted L2 norm. These are if and only if conditions. So that's well known in the numerical integration literature, but not well established in the control field. Now, I refer to perhaps, well, I don't know, I'm calling this one-sided Lipschitz condition, differential one-sided Lipschitz condition. They are equivalent provided the map is differentiable. If the map is not differentiable, the first condition still holds as a way of defining contractivity. And the 2 of them are, of course, equivalent if and only if to a differential incremental stability condition. So this is an ordinary differential equation, well, differential inequality here describing how the distance between 2 trajectory evolves. This is a Dini derivative. The distance between the 2 trajectory is exponentially decreasing, essentially. That's what that's saying. And you can write integral versions of this very, very easily. So this is the first of 4 slides on this topic. Let me briefly mention that if you have a strongly contracting vector field and you additionally assume that it is the gradient of a function, then that function, it's if and only if that function is strongly concave. So there's really very tight connection. In other words, the function is strongly concave if and only if minus its gradient is strongly contracting. And F is a monotone operator if and only if minus F is a strongly contracting vector field. So there's very tight connection between convex optimization monotone operator theory and contraction theory. Now, it should come as no surprise that if a vector field is strongly contracting, then the flow is a contraction and there exists a unique equilibrium point, and those are the 2 Lyapunov functions that I promised you earlier. Finally, what's interesting is that precisely very simple Euler integration of the ODE with appropriate step sizes allows you to design a Banach contraction to compute the equilibrium point of the ODE. And for clarity, when I pick an alpha and I design the Euler integration, this is exactly the same as, okay, I have a vector field F, I'm looking for a 0, I translate F, I obtain a new map G, and that finding an X which is a 0 of F is the same as finding an X that is 0, sorry, there is a fixed point of G, that was the whole point. And the Euler integration is exactly the same as the average integration that I talked about earlier. So it's really just the same. I'm changing notation. G as a fixed point problem, F as an equilibrium point, but it is the same. And what's known in this area, this is not my result, it's a classic result, is that if you have a map F F, and it has a contraction rate C, Lipschitz constant L, and you can define a condition number. Then what's known is the range of alpha for which the average iteration is a contraction, as well as the optimum value of alpha and the corresponding minimum contraction factor. This is all known with respect to the 2 norm. As you know, I stated my interest for the L infinity norm, and I'll motivate it better in the second half of the talk. Our recent results are how do you generalize this contraction theory, these 4 slides that I've just showed you, to the case of L1, L infinity, and other non-Euclidean norms. So how do I achieve this? Well, in the Euclidean case, I was using an inner product and I was using LMIs. I need to generalize inner products to norm spaces that do not have inner products. And I need to generalize LMI conditions to conditions on something called logarithmic norms. And so here's one interesting thing you can do. You can define this 1 pairing and infinity pairing, as well as you can define the L1 logarithmic norm and L infinity logarithmic norm. So let me talk just for a second. So the logarithmic norm associated to a map, to a matrix, a number. So they're an operation on the matrices, you get a number out of it. And instead the weak pairing, given 2 vectors, generate a scalar. All right, so what are these operations? Do you need to, I don't want you to certainly study them through my slides right now, but logarithmic norms are relatively well established. And I want to make a case when you're looking at the 2 norm, if you impose a condition on the logarithmic 2 norm, that's the same as asking a linear matrix inequalities to hold. And if you're asking for the infinity norm, this is simpler. This is just a diagonal dominance linear inequality. So we're going from LMIs to linear programs when we go from 2 norm to infinity norm. Log norms are convex in the arguments and quasi-convex with respect to the weight selection in some cases. And that turns out to be important. What are weak pairing? Weak pairings are generalizations of inner products. They are not linear, but they are sub-additive. They're homogeneous, positive homogeneous. They give rise to a norm, and they satisfy Cauchy-Schwarz inequality. And the sign and max pairing that I defined earlier satisfy those properties. Moreover, they enjoy 2 interesting properties. The relationship between log norms and weak pairing is very strong. For example, the log norm is the maximum value of this quadratic generalized form in A. And the other thing is that the weak pairing appears whenever you take the derivative of the norm of a curve. So you have a curve, function of time, take the norm, take the derivative. Naturally, the weak pairing appears in there. So this is referred to as the Lumer inequality, and this is referred to as the Daimling equality. Actually, pardon me, they're both equalities, of course, Lumer's and Daimling's equality. Anyway, the bottom line is just that this slide here, you should remember, is exactly the 3 conditions as before for the Euclidean case. What is the one-sided condition, the differential one-sided condition, and the differential incremental stability condition? It's exactly generalization in the L2 case, in the Euclidean norm case. These are exactly the ones as before when you plug in the formula, but now they work for arbitrary L1 and infinity, or actually for any norm space for which you can define a proper weak pairing and log norm. Perfect. So we're going to be worried about computing these log norms of Jacobians and what follows. Before I proceed, I'm interested in fixed point strategies, right? So how do I do that? It's the same as before. You have a certain contraction rate, Lipschitz constant, and condition number. You can write theorems on the range of alpha for which the Euler integration of the vector field or the average iteration of the translated map are a Banach contraction, as well as you can compute optimal values of the step size and of the contraction factor. These are general formulas that hold for any norm. In the papers, we have additional simplification for the case of the infinity norm. And so you get even larger step sizes and smaller contraction factors. In that case, there's like a magic lemma that simplifies calculations even further. So, okay, now, so this is the conclusion of the first part of my talk. I have shown to you contraction theory in for ODE. How do you check it? And based on that, how you design fixed point strategies. These are average iterations. And as you recall, they come with robustness guarantees that I talked about. So now I should talk to you about how do I use this for neural networks. So I'll do that. Before I do that, let me take a small detour. So I'm interested in networks in general. You know, I've been studying for many years dynamics of multi-agent complex network systems that arise in science and technology. And typically, we're interested in relating the network structure to the network function. For this particular talk, for sure, we're talking about dynamic behavior. And so let me show you some ideas that go in this direction, even though the full path is not yet complete, and I can elaborate on that. So how do you achieve this ambitious picture here, by the way? So, you know, people have used general Lyapunov theory, certainly very powerful, the approach based upon passivity, dissipativity. A smaller community has worked on monotone dynamics. One of the claims of my presentation is that contraction theory, in fact, is a very natural and powerful approach to handle all of these cases. Let me show you how you would go about it. So here is a new little result that I don't know that people are familiar with, which we obtained 2 years ago. So imagine you have a collection of subsystems which are interconnected. Xi is the state of the IS systems, and X minus I is the state of all other states, right? So all other states that are connected to I. So this is a usual notation in game theory. So Xi is the IS state, X minus I is the state of all the others. So suppose each subsystem individually, when essentially at fixed neighboring values, suppose each subsystem is strongly contracting with rate Ci. Now, suppose that the dependency upon the neighboring values of the dynamics of the ith node is Lipschitz. So in other words, there exist gain coefficients gamma positive, gamma ij, such that this Lipschitz bound holds. Now, take all of the contraction rate, put them on the diagonal of a matrix. You have n subsystem, each of them is contracting, so you have n negative numbers. And then put all of the gains in the off-diagonal entries of your matrix. Now that matrix is a Metzler matrix. It's called a gain matrix. If that Metzler matrix is Hurwitz, this can be stated as a small gain condition. If that Metzler matrix is Hurwitz, then you can easily show that the interconnected system is infinitesimally strongly contracting, with the rates equal to the spectral assisa of that matrix, or minus the spectral assisa, and with respect to a family of norms. So if you have contracting individual subsystems and you interconnect them, this is a sufficient condition for contractility. Now, in general, however, many network systems are not contracting. For example, here's a beautiful little result. If you have other conservation or invariance under a group action, then the Jacobian has to have an eigenvalue equal to 0, and the one-sided Lipschitz constant is automatically guaranteed to be non-negative. If additionally the dynamics is monotone in the Kamke-Muller sense, not in the sense of monotone operator, then one can actually show that the one-sided Lipschitz constant is 0. So in other words, there are many systems that are weakly contracting in the sense that their one-sided Lipschitz constant is less than or equal to 0. And while I'm not going to show it today, there's a theory that developed for weakly contracting systems and all of the examples to which it applies. Alternatively, it's also possible to look at problems where instead of using a norm, you use a semi-norm in defining your contractivity property. And the theory carries through to that case as well. We can define a one-sided Lipschitz semi-norm, and there are consequences for the dynamics with regards to that. And here are several examples where this is applicable. And both weak and semi-contraction papers originate, weak and semi-contraction ideas originate, they could be back in time. There was a 2005 paper by Wang and Slotin talk about weakly contracting systems and semi-contracting. We also have a TAC paper about to come out on this topic. And finally, also I think very exciting are recent developments on K and alpha contracting systems, which I will not talk about here, but that I think are relevant in this broader picture. Okay, I've taken my detour. I have another 20 minutes. Let me now abandon network systems and go back, general network systems, and go back to recurrent neural networks and applications of these two machine learning problems. So I'll do it in two steps. First of all, in the literature, there's a number of models that have been studied as continuous time recurrent networks. The Hopfield neural networks in the early 80s and its close relative, the firing rate model, are described by ODEs of this form. If you observe for a second the firing rate model, and you look, for example, for an equilibrium of the firing rate. Well, this is exactly the implicit neural network that I talked about at the beginning of this lecture, right? Because if you look for it, so the firing rate model is exactly, remember, if you call this G of X equal to X, then I also define a map F, which was G, well, identity map plus F was G. So the firing rate ODE is exactly the one associated to the fixed point neural network that I thought, implicit neural network that I talked about earlier. Now, as I said, in the literature, there are other models, for example, the Hopfield, Persitsky types, and many others. This is a I'm going to focus, because I need to go back to implicit neural networks, I'll focus on the firing rate in what follows. However, the general approach applies to each of these dynamics, and it's discussed in an upcoming ACC 22 paper that will appear in a couple of months. Now, each of this model is equipped with the activation function. Let me talk about the activation function for a second. Activation functions can be only locally Lipschitz. They don't need to be differentiable. They are usually slope restricted, meaning to say their derivatives are upper and lower bounded. And if the map is only locally Lipschitz, what I mean by that is I mean to say the variation. And I will take them 0, 1 in some example, but the entire theory works for arbitrary for dmin dmax where dmin is non-negative. So for slopes between a minimum and a maximum value. I let the plus symbol denote the ReLU map. And once again, it's a diagonal nonlinearity. What I mean to say, if you feed into it 2 arguments, you get 2 outputs, and on each output is applied a scalar nonlinearity with this property. Let me mention that in some cases, the activation function takes all of the values between the minimum and the maximum slope. In other cases, maybe that's not true. But if the activation function, the derivative of the activation function is surjective in that set, then I have stronger results than what follows. All right, so let me make 2 very simple mathematical observations. Suppose I wanted to compute the one-sided Lipschitz constant of the firing rate. Then I need to take the Jacobian of the map, which is very easy to compute. And I need to worry about the largest, the value that the log norm takes over all possible points in space. But this Jacobian of the activation function is a diagonal matrix, and each entry along the diagonal takes values between dmin and dmax. An unknown d taking value between dmin and dmax for each entry. I can also bring out the -1, so that's not a problem. And what I obtain is an expression of a log norm over a hypercube, Now, it turns out that you should know, if you're trying to maximize a convex function over a polytope, such as an hypercube, you should know it's equal to the maximum value over just the vertices of the convex polytope. But in this particular case, one can show that instead of checking 2 to the n vertices, in fact, the problem reduces down and you have to check the log norm just at 2 vertices. So there's a big simplification that occurs here. And so here I have formulas which, I don't want you to understand, but I just want to make the point that in this formula, there are 2 terms, 1 and 2, and you take the max of them. That's because you're maximizing a convex function, and instead of having 2 to the n vertices, there is a simplification, a key one that appears, just 2. One additional comment: if the activation function is the slope is surjective in the value dmin dmax, then here, which I wrote this as an upper bound, but in reality, this analysis becomes tight. In other words, it's absolutely not conservative. So it's sharp, no conservatism. Wonderful, wonderful. So, okay, so the next slide here, I apologize, I confess I meant to simplify it some more. Let me not get you scared by the too many formulas here. So I have the firing rate dynamics. I made it even more general now. I have an arbitrary set of dissipation rate C. The one-sided Lipschitz constant, now I do it also with respect to a set of weights. And it's just these 2 values. Moreover, I mentioned that log norms in some cases are quasi-convex with respect to the weights. So here I define a linear program with respect to which I can compute the optimal weight. And ultimately, after all is said and done, in many cases, I can write the Lipschitz, one-sided Lipschitz constant with respect to the optimal weights. I can obtain that value by just looking at the spectral assisa of appropriately defined matrices. So that there's big simplifications that happen here. It's on the archive. It's in ACC 2022, and it's just how do you make this machinery work for the type of nonlinearities that appear often in recurrent neural networks. Now, I have talked to you about contraction theory. I've talked to you about how do you apply it to recurrent continuous time neural network. Now I would like to talk about machine learning applications for the remaining time. So I would like to talk to you about this idea that we are interested in going from feed-forward to implicit and recurrent models, from multiple layers to a single layer, which is a fixed point problem. Why are we interested in this? Well, first of all, I've already said that it's bio-inspired. I believe it's true. I mean, I'm not a neuroscientist. I am actually looking to collaborate with some neuroscientists, but I believe it's true that biological neurons are not connected in a clean feed-forward structure. Rather, let me emphasize this. Rather, if you were to write a synaptic matrix A, the first model, the feed-forward model, is tantamount to having non-zero entries in a synaptic matrix, which are only on the upper diagonal. Whereas in biological systems, beside the upper diagonal entries that I'm marking here in blue, there also are out-ups connections, which are on the main diagonal. There are skip connections, which are up there, and there are feedback connections that are on the bottom left. So the synaptic matrix describing the interconnections between the neurons in a biological system may well be full or all-to-all or certainly dense, rather than sparse and extremely highly structured as in a feed-forward architecture. And by the way, clearly having multiple layers like that, or writing a single comprehensive equation is equivalent. If I take A that has upper diagonal structure, the second equation becomes identical to the first here. Okay, so so it is a generalization. So if I go back here, when I go from left to right, I'm only generalizing the models that I study. It's more models, not less. But there are other advantages. One is the simplicity in analyzing these models. And there have been papers published in leading machine learning conferences that have extolled the virtues of this implicit architecture in terms of accuracy, in terms of memory efficiency, and in terms of input-output robustness, which is something I'm going to talk to you about. The results I'll show you were in our recent NeurIPS paper. So okay, so let me give you some more motivation and inspiration. So as I said, if you go from feed-forward to the implicit model, you're generalizing for sure. The second idea is the following. When you're talking about deep neural network, you're talking about having many layers. Perhaps K is very large. Now, in machine learning, people have studied this concept of tying the weights. In other words, instead of having a different synaptic matrix at each layer, because you have a growing number of layers, the idea is let's use the same sets of weights. That's weight tying. But if you are going to weight tie a deep neural network, now what you're doing is you're applying a large number of times the same map. But then perhaps what you're doing is just leading to the fixed point of the equation. And so in other words, weight-tied infinite depth neural networks is exactly the same as the fixed point architecture that I'm illustrating, exactly the same. And finally, there is also this concept in machine learning, this architecture based on solving neural ODEs. And the neural ODEs would be exactly the firing weight ODE that I talked about. And in the neural ODE architecture, machine learning scientists select particular times at which to stop the ODE. Here, instead, I'm allowing time go to infinity so that I reach the fixed point. All right, so these are all interpretation equivalences. For those of you who download the slides from my website, they will be there shortly. These are several references to implicit models, and I would like to acknowledge and thank Ian Manchester for his wonderful talk that he gave to my group and at UC Santa Barbara year and a half ago, something like that, which got us started in this direction. Now, one more thing you should know: how do I train implicit neural networks? Right, the standard approach would be to set up a loss function. You're given some training data. So this is a supervised learning problem. You minimize the loss, and you have now a constrained optimization problem. So it turns out that the hidden is not the right word. The latent state of the neural network becomes part of the optimization. And it turns out this is not our work. It's understood. You can do efficient backpropagation through implicit differentiation. And you can use the stochastic gradient descent, but you need to keep in mind that at each step you need to solve the fixed point equation. We have not forgotten about it. So essentially, if I want to make my implicit neural network a practical learning architecture, I need to endow it with some algorithm. For example, algorithm to compute fixed points very quickly for large-scale problems, right? Even before that, do I know that a fixed point exists always and it's unique? So I also need to impose some conditions for well-posedness of the problem, right? So these are interesting challenges. Let me elaborate. And here are two more challenges. So suppose you're considering images that represent digits. So then perhaps my nominal image is correctly classified as the number 8. But it is well known that this classifier can be very brittle, very fragile, sensitive to disturbances and noise. And a small amplitude disturbance can mislead the classifier onto a wrong label. Small input changes cause large output changes. This is in fixed point theory, this is called precisely a stability problem. In controls, I would call it maybe a robustness problem. And one strategy, which I'm going to talk about today, but there may be better ones. One strategy is to look at the input-output sensitivity, input-output Lipschitz constant. In numerical analysis, people call it the condition number. How do I make sure that if you apply a small input, maybe I have a small change in the output, and then when I apply the final softmax to do the classifier, perhaps I continue to classify the image as an 8 instead of a 3. And so let me clarify also, there's a famous paper by Goodfellow 5 years ago, sorry, 2015, 7 years ago, about 1,000 citation, essentially saying that L infinity norm constants are better measures of the impact of perturbations and in the inputs and quantization in the synaptic matrix, for example. And so therefore, two more challenges when you are studying these implicit architectures for machine learning, supervised learning, two more challenges are how do I analyze, how do I certify the correctness of my neural network? That's an analysis question. And then possibly, how do I change my design? How do I embed the robustness in the design to start with, right? So I have several challenges that I have outlined in order for this implicit or fixed point neural networks to make sense. And it turns out that they're all immediately answered by contraction theory as applied to the recurrent neural networks that I showed to you earlier. In other words, I am interested in this implicit neural network computing a fixed point. But that's the same or very closely related to the firing rate recurrent neural networks. That's the associated ODE. And both of them are closely associated with the average iteration, the Krasnozelski man also called, or the forward Euler step. And what have I shown to you earlier? Basically, what I've shown to you earlier with all of the, in that slide, where I left a bit too many equations, when everything boils down, is if you select, for example, remember I had a D mean and D max, and I will set them equal to 0, 1 here for simplicity. Then it turns out that it's just a very simple log norm condition with respect to the infinity norm. So it's a diagonal dominance condition on the entries of A. It's an unbounded convex polytope in the set of matrices A. And if that condition is satisfied, then many things happen. The dynamics is strongly infinitesimally contracting with the given rate. That automatically implies existence and uniqueness of the equilibrium of the dynamics at the fixed point of the problem. So that was the first challenge. The second challenge is, how do I compute this fixed point? Well, I can tell you what is the optimal step size and what is the minimum contraction factor. And with those selection, the average iteration is a Banach contraction. So it comes with all of the nice properties of Banach contractions. And moreover, I showed you, remember, that Lim's lemma and the generalizations, and I can write down a formula for the input-output Lipschitz constant, which allows me directly to do certification and analysis of the implicit model. There was one last challenge left out, which is how do I embed the robustness into the design? And so here, this is very traditional, nothing perhaps surprising. First of all, you need to add not only the fixed point equation, but also the well-posedness constraint, right, in the design problem. And moreover, if you want to minimize the input-output Lipschitz constant, then you introduce a regularization parameter lambda. When lambda is 0, it's the old design. When lambda is positive, you pay a price for having a large input-output gain. And gamma here, you know, it's less than 1, so it's a hyperparameter, and you can experiment as people naturally do in machine learning problems with optimal or with efficient choices for such a hyperparameter. By the way, I should say that this constraint here, we have results on both. How do you optimally project onto the set of matrices that have log norms upper bounded by gamma? So you could have a projected gradient descent, you take a step of the gradient and then you project it into the constraint set. So in order to execute that efficiently, you want to know how to optimally project. Alternatively, you can also parameterize this constraint, and it becomes a relatively straightforward a parameterization. It's very straightforward. It's much simpler than parameterizations that are obtained when LMI conditions are required. Okay, let me conclude my talk with some numerical. One last idea. If you were to perform dropouts throughout the computation, the training, Then it turns out that this theory is no problem whatsoever, because well-posedness naturally follows. So if you have a log norm with respect to a monotonic norm, if you select a submatrix, a principal submatrix of the matrix that you're given, then in fact the log norm can only decrease. So you're entirely fine. Similar, as time allows, I can talk to you about the type of errors that occur when there are other structural perturbations to the system. They're all very well handled by non-Euclidean contraction conditions. Okay, so the empirical results are, I'm going to show you, are with respect to MNIST, which is the standard handwritten digital data set. 60,000 images for training, 10,000 for testing. Each image is grayscale, 28 by 28 pixels. These are some examples. And the order of the neural network is 100. So at each step, every time you need to repeat a fixed point, you had a 100-dimensional problem to solve. And there are two types of plots that I want to show you. One is a Pareto optimal curve, which shows you if you have a certain test error on the vertical axis, you trade that off against the Lipschitz constant. So if you don't put any lambda regularizer, then you are perhaps here. As you introduce the regularizer, you go up on the Pareto optimal curve. Our design at lambda equal to 0 is very closely comparable to previous design in the literature. As we introduce our lambda for the regularizer, the Lipschitz constant drops immediately by orders of magnitude, and then it drops more, but then the test error goes up. So of course, it's a Pareto optimal curve. It's very natural. Now, this image on the left is perhaps not all that interesting. This is just telling you that the Pareto optimality problem, where I have that hyperparameter, the regularization parameter works correctly. What's more interesting is plotting accuracy of the classifier, so accuracy on the vertical axis, versus imagine that I have a perturbation, and I designed the perturbation using some state-of-the-art machine learning techniques, and I measure the amplitude using an infinity norm, and then I compare various solutions. So the colorful blue and red and even green are essentially previous solutions. Well, actually, to be accurate, the red one is our work. The green and blue are solutions in the literature, and I want to mention to you that they drop rapidly, although they start very accurate. You start very accurate, so an accuracy close to 100%, and then you drop rapidly. In our model, as you increase the regularization, performance drops in the neighborhood of 1. But then, as you see, it remains high for larger perturbations. Let me show you this better. So here's an example. So here at disturbance of magnitude 0.2 in infinity norm, our solution for lambda equal to 10 to the minus 25 preserves 80% accuracy, whereas by now the previous results to which we compare had already dropped to 20%. So you're trading off, perhaps you're trading off clean performance where there is zero perturbation with performance at corrupted images. There's a lot more that needs to be understood about this. All right, I have concluded. Let me give you my conclusion and future and ongoing research. I've shown to you a deep connection between contraction theory, monotone operator theory, which is a synonym for fixed point theory, and essentially convex optimization. These are effective methodology to handle control, optimization, and learning problems. And I have hinted at you, I didn't have time, that they also work for complex, large-scale nonlinear network systems. Strictly speaking, the first contribution was how do you do the non-Euclidean case? And the other contribution, was this analysis of recurrent neural contractivity analysis of recurrent neural networks, as well as then the application to machine learning. The code to generate the images is available at this GitHub location, and the slides will be on my website, half an hour from now at the latest. You can search for my last name. You should be able to find it. And I will just say that if time allows, what time is it? 56. That already on the archive, there's some extension collaboration with Sam Coogan and Matthew Abate on mixed monotone contraction theory. and other extensions that we are working on. And with that, I would like to thank you all for your kind attendance, for your and I would welcome your input or questions in any form, shape, or form. Right now, time is the essence. If time we get disconnected, please feel free to send me an email. I will send you my Zoom address, and we can continue the conversation past the hour.
Thank you so much for a wonderful talk. And some of you will meet with Francesco in the afternoon at 4 p.m. Eastern time. So we are going to continue, with more scientific discussions. We have time for a couple of short questions. So any question from audience, you can unmute yourself or type your question in the in the chat box. Any questions? Okay, maybe let me ask you one question here. So I think your contraction theory, to networks is very interesting. Okay, does it have any connection with the diagonal dominance principle, in decentralized systems? So you assume the off-diagonal elements are part small,
Yes, Dongping, it's closely related. So the Metzler matrix is Hurwitz if and only if it is quasi-diagonally dominant. So there exists a set of weights with respect to which, after scaling, it is diagonally dominant. So yes, if you have, so that is typically the condition that you obtain when you are using these non-Euclidean norms. Yeah.
Very good. So if you deal with networks that have a non-contractive subsystems, so you can use feedback to make contractive, right? So you have systematically to do it, right?
That's exactly right. So you can imagine you've applied feedback. So you're looking at the error system, and you apply these techniques to that.
Very good.
There are some results. I want to mention Slotin Jean-Jacques has results on that, talking about skew symmetric interconnections. With respect to the L2 norm. Those also are known to work. One has to set it up correctly. I think it's a great question, Dongping, and I think that there is more than can be done and that we should understand in this area.
Great. Okay. I think the time is perfect. Okay. Now, so if there's no more questions, then let's thank speaker again virtually. Thank you, Francesco, for a great talk. I look forward to talking to you in the afternoon then.
Thank you all. And if any of you wishes to talk with me some more, please drop me an email, and I will be near Zoom for the next hour or so for sure.
Yeah, if
any of you who are not already on my calendar.
Sure. If any of you want to join our group meeting at 4 o'clock, please send email to Raquel. I think she can send you a Zoom link, for you to join us.
Professor, there's a question for you in the chat box.
Yes, yes. Dongping, is there time or should I?
Yeah, we have time. Yeah, please.
So, thank you, Zara, for your wonderful question. I have seen papers on approximating limit cycle. For example, there was one by Sam Coogan and Michael Margaliot very recently. There is also a paper by Amritam Das and Rodolphe Sepulcher relatively recently. Clearly, the problem is more complex. Clearly, the problem is more complex. And also, I think there were results along those lines in the work by Pavlov and Nichemeyer and co-authors in the context of convergent systems. So it's a longer story, and I myself haven't yet published on it. So, but I know there are recent references. It's pretty exciting. And actually, let me continue one more comment related to your work, Zara. It would be very interesting to compute steady state PDFs for stochastic ODEs, perhaps having fast algorithms to do that. Because, for example, in machine learning, there's a lot of interest in stochastic gradient descent. And right, so yeah.
Good. Okay. I think okay, now maybe due to time constraint, we can end here. So thank you one more time, Francesco.
Thank you,
for the
Dong.
one.
Thank you very much.
Talk.
Yeah.
Okay, talk to you later.
Bye-bye, everybody. I hope to see you all in person soon.
Yes, thank you. Yeah, bye.
Bye-bye.
Take care.
Thank you so much.
Thank you.